people have used and animals have used the ground for many years, taking advantage of the energy stored in the ground. The ground is warmer than the air outside in the winter, cooler than the outside air in the summertime. What we need to do is basically bury plastic pipe in the ground in order to build basically a heat exchanger in the ground, circulate fluid through it, run it through a heat pump. The heat pump either cools the water and warms the air that's going to the building, or cools the air and rejects the heat to the ground. A lot of people perceive geothermal systems as expensive, risky, but they are aware of the potential energy cost savings and the reductions in CO2 emissions. Energy cost, if you're a building owner, this is a fairly important reason for many building owners to select a geothermal system. This is typically you're looking at energy cost reductions, even with fairly inexpensive gas, fairly expensive electricity. We're looking at 40 to 45% savings in energy cost. Return on investments. There's a number of many projects that have been done with simple paybacks of 4.7 years. Returns on investment as high as 25 to 30%. Is it good for the environment? Basically looking at because it uses electricity, it depends to some extent on how electricity is generated. Even in a place like Ontario, there's where the electricity is not particularly clean, we're looking at a reduction in CO2 emissions of about 65 to 70%. In Manitoba, we're fairly fortunate because the electricity is very clean. We're looking at about a 99% reduction in CO2 emissions compared to using natural gas or other fossil fuels. Even the best gas boilers can reduce CO2 emissions, but you're looking at maybe 10 to 15% reductions, depending on what's being replaced. What's in it for the utility? For an electric utility, there's some fairly large benefits. Basically, what it does is reduce electricity demand, peak electrical demand, kilowatt demand. In this a typical building, we're looking at about a 40% reduction in kilowatt demand. That's a fairly big deal because building hydroelectric dams or even gas generating stations costs anywhere between probably in the range of about $3,000 per kilowatt. Last numbers I've heard on building kiosk is about $12,000 or $13,000 per kilowatt. That's enough energy to run your hairdryer. At the same time, in reducing the electrical demand, it also increases electricity consumption. So there's more revenue for the utility, because electricity is being used not only to cool the building, but it's also being used to heat the building in the winter. Interesting fact, in Manitoba, there's about 130,000 single-family homes that are heated with electric resistance heating, mostly outside of Winnipeg, but there's 130,000 of them. To convert, if all of them were converted to a geothermal system, that would reduce electrical demand by about 900 megawatts. Even if it cost about $30,000 per home to install the systems, you're looking at a cost of just under $4 billion, or about $4,350 per kilowatt. Kiosk will produce 695 megawatts. It's costing, last I heard, about $10.5 billion, or about $15,000 per kilowatt. So reducing demand with energy-saving devices such as a geothermal system is much more beneficial to the whole Manitoba economy. So if they're so good, why isn't everybody using them? One of the problems is that rules of thumb are often used to provide a quick answer to a client. Rules of thumb they're typically not accurate. They're over and often result in a system that is too large and is perceived as too expensive. Equipment is sized basically on so many tons of cooling or heating per square foot of building, or per 400 square feet of building. And then the size of the ground heat exchanger is simply multiplied by the number of tons that is, as is suggested by the first rule of thumb. Best rule of thumb is chop off the thumbs. Start doing some proper design methodology. Just as an example of that, if we're looking at 3 buildings, they may have identical heating and cooling loads. In this case, a cooling load of 480,000 BTUs per hour, or about 40 tons. Heating load may be a little bit lower, 385,000 BTUs per hour. That would suggest you'd need about 40 times 200 feet of drilling, about 8,000 feet of drilling. So if we look at just the peak loads, all 3 buildings are identical. The difference is when you start looking at how many hours the systems in the different buildings are operating per year, you're going to get a much different result. The church is going to be basically looking at cooling on Sunday mornings for a couple of hours. That's what's going to be driving the cooling load in the church. The peak load might be the same, but it's only going to be running, maybe 3 or 4 or 5 hours per week. Retail store, if it's open 12 or 14 or 16 hours per day, that system is going to be running a lot more because there's always a lot more people in there, and there's also a lot more lighting. So it's going to be cooling many more hours. The apartment building is probably going to be somewhere in between there. People are going to be in there much of the time, so they're going to be using some cooling more than the church, but probably less than the retail store. If we look at the heating loads, those are going to be quite a bit different as well. Church is going to be, because it's empty, there's no heat gained from lighting or from people in the building. So that building is going to be requiring heating for many more hours because it's only used a few hours per week. Retail store, because you've got a lot of people in there and the lighting is turned on, there's a lot of activity in the store. The heating loads are going to be a lot smaller, and at least the heating loads that are going to be seen by the ground heat exchanger. The apartment building is a bit different. It's going to have much more equal loads. The other thing that needs to be considered is where the electricity that's being used to power the compressors and the circulation pumps, where is that going? When you're cooling the building, you're taking out the heat from the building and adding the heat from the compressors to the heat that's going into the ground. So you're adding more energy to the ground than you're actually taking out of the building. The reverse happens when you're heating the building. Some of the heat that's being delivered to the building is being contributed by the circulation pumps and the compressors. So the difference, basically, looking at is how much energy is being pushed into the ground by the system and how much is being pulled from it, what the energy balance is. Both the first two, the church and the retail store, are both fairly unbalanced loads. Even though the peak loads are the same, the amount of energy that's going into the ground or being pulled from it is quite a bit different. The apartment building, the loads are almost identical. So if we look at what happens, if we're looking at a typical rule of thumb, 40 tons times 200 feet of drilling per ton is fairly common in many areas. And if we do that, we're looking at about 8,000 feet of drilling. So the difference is the temperatures that the ground heat exchanger is going to operate. What's going to be delivered to the heat pumps to heat and cool the building? What do they have to work with? So the church is going to get fairly cold. Typically, a system is designed to operate, or most heat pump equipment is being designed to operate at between about 30 degrees Fahrenheit or about 0 or minus 1 degree C, and no higher than about 85 to 90 degrees Fahrenheit or about 35 degrees C. So what's going to happen in a building that we're extracting a lot more heat from the ground than we're putting back in is that ground loop is going to cool off over time. The opposite is going to happen with the retail store, where we're rejecting a lot of heat to the ground, and it's going to get too warm. Whereas the apartment building is going to be just about right. And this is only going to get worse over time. If we're looking at what's going to happen over a 10-year period, the temperature of that the ground loop for the church is going to gradually drop a few degrees. Retail store is going to gradually increase a few degrees. And one of them is going to get too cold, one of them is going to get too warm to operate efficiently. And they could even get to the point where the heat pumps aren't going to work. Whereas looking at the apartment building, because the loads are more balanced, you're pulling out as much energy every year as you're putting back into it. So there's much less danger of that ground heat exchanger to overheat or cool off. And even if you extend the time period by increasing the size of the ground heat exchanger, we started out at 8,000 feet. We've added about 1,200 or 1,300 feet of drilling to it. You're still going to get down to the point after about 10 years where it's going to start getting too cold. If you make it even larger, get it almost to 11,000 feet, it might take 20 years, but it's still going to get there. You're simply delaying the inevitable. Same thing with the retail store. If what you're doing, increase the size of the ground heat exchanger to 11,000 feet of drilling, add about 30, 35% to the size of the ground loop, it's still going to get there after about 10 years. After 20 years, even adding another 5,500 feet of drilling, you're still going to get to the point where it's going to get overheat over time. Whereas the temperature of the ground heat exchanger for the apartment building, because the loads are so much more balanced, it can keep on going for the life of the building. So what that kind of implies is that if you can change the building heating and cooling loads and heating and cooling requirements by doing things like changing the type of glass that's specified, by changing how the ventilation air is supplied to the building, by what kind of lighting system or lighting system controls are going to be supplied to the building, you can actually change the amount of heating and cooling that you need in the building and allow it to work a lot more effectively with the ground heat exchanger and basically for the life of the building. So looking at sort of a summary of how much difference it can make is that even by making the ground heat exchanger 37% larger, it's still going to look at potentially failing after about 20 years. And for the retail store, it's making it even almost 70% larger. It's still going to fail. But if your energy loads are balanced, then the size of the ground heat exchanger can be much smaller. In this case, about 13% smaller than what the rules of thumb would suggest. So a lot of times what happens is that these systems are perceived as too expensive, is they may be bigger than they need to be, or they are going to fail because they're not large enough to deal with the unbalanced loads that they're designed for. So again, cut off the thumbs if you're designing a system like this, because the designer of the ground source heat pump system is really designing the energy source. It's much different than connecting to, let's say, a gas line where the gas utility is supplying the gas. You open the valve, pay the bill, and you're going to get as much energy as you need to for as much time as you need to. So looking at a hypothetical project, this is based around the Dakota Community Centre in Winnipeg. There's 2 ice rinks, and connected to the ice rink is a community center. Across the parking lot from it is a library, about 15,000 square feet. Beside the library is a school, about 60,000 square feet. And looking at what can potentially be done with a system like this by moving energy around from one building to another, gas use and the related CO2 emissions can be eliminated from roughly about 200,000 square feet of building, the school, library, community center, and the personal care home, plus about 109 single-family homes that are surrounding this field. So basically, if you look at where the energy is coming from and what can be done with it, an ice rink, by its very nature, has to get rid of a lot of heat. And if you ever pass an ice rink, past the cooling tower, you can see that steaming away all winter long. That's heat that can be potentially recovered and recycled either within the building or to other nearby buildings. Looking at the community center, if the energy load profile that you would see with most buildings in our climate, in Winnipeg, for example, we're going to do a lot more heating over the year for a lot of buildings than we are looking at cooling. This is the amount of heating In the blue is the amount of cooling that is needed on an annual basis. The red area is the amount of heating that's needed over the year. The solid red line is what the peak heating requirement is in each of those months, and the peak cooling requirement in each of those months. So looking at a 24,000 square foot building, it is going to pull a lot more heat from the ground than we're rejecting to it. But even a building that size, it barely makes a dent in the amount of heat that is being rejected by the two ice rinks. So the small dark area right at the bottom is how much heat we're taking, that we would take from the ground loop, compared to how much heat is being shoved into the ground. If we tried to design a ground loop based on those energy loads, even with 45,000 feet of drilling, we simply can't use all of that heat. That ground is gradually going to become saturated with heat after about 10 or 15 years, and it's going to become unusable. If we look at the library adjacent to the building, it's got higher cooling loads than it does have heating loads, and that's partly because of how the building might be used, the amount of glass that's on the building, things like that, and but it can be added to the system. Adjacent to the school, up 60,000 square feet, 5,600 square meters, that's adjacent to the library. Again, is much more heating dominant, not used much in the summertime for cooling, but so we're extracting a lot more heat from the building from the ground than we're putting back into it. So if we look at what happens to the overall load profile of the three buildings, the ice rink, community center, the library, and the school, we still have barely touched the amount of heat that is generated by the refrigeration plant that's in making the ice for the building. Again, we're still looking at the same kind of long-term temperature increase. Adding a little bit of borehole, doesn't accomplish enough. It's going to fail after probably about 10 years or so. There's a personal care home adjacent down the street from it, adding about 80,000 square feet of space. Again, extracting more heat from the ground than we're putting back into it. Load profile is better, but we're still rejecting a lot more heat to the ground than we're pulling from it. Adding a bit more borehole, again, that sort of extends it out a little bit. We haven't had to add much borehole, even though we've added close to 200,000 square feet of building to the system, but it's still going to fail after about 10 years. So looking at the space around there, there's a lot of single-family homes in that area right around that. Looking at what the energy load profile looks like, we're all aware of how much heating that we need to do and how little cooling we need to do in homes, a typical single-family home in Winnipeg. Much more heating is required than cooling, and that's simply because commercial buildings have a lot more lighting and a lot more occupancy in it than a typical single-family home. Homes are basically, the energy loads are basically based on what the climate is doing or what the weather is doing outside. So looking at typical homes around there, they're all very similar. The numbers are a bit different based on the size of the home, but they're all going to be extracting more energy from the ground and then they're putting back in. So if we look at the types of homes that are surrounding this field, in this area that's highlighted, there's about 26 homes. We can add these loads to the overall loads of the ice rink and the four other the community center, the library, the school, and the personal care home. What that does to the overall energy load profile is basically it increases the amount of heat that we're taking from the ground and how much we're putting back into it. What that does to the ground loop, not adding a single foot of borehole, we've added 26 homes to it, and we're still overheating. In total, there's about 109 homes in the right adjacent to the field that the recreation center is built on. So if we look what happens to the energy load profile on that, now we're starting to get some real heating loads that we're actually going to start taking some heat from the ground and start absorbing some of the energy that's being shoved into the ground by the refrigeration system. So what happens, because the loads are much more balanced, we've added 1,000 feet of borehole to it. And after 10 years, we're starting to get to the point where, and a very slow increase over 10 years. So if we look at all of the systems, how they can be connected to that, if a system is designed with a single pipe circulating around behind the houses and is connected to the ice rink, to the community center, to the library, to the school, and to the personal care home, and then individual connections to each of the single family homes surrounding it, and locate the ground heat exchangers at intermittent locations around the pipe. So what can happen on a system like this is that we're trying to manage the temperature of the fluid circulating around, connecting all of the buildings. There's going to be a lot of times when there's roughly the same amount of energy going into this pipe from the ice rink that the other buildings are taking from it, and we don't need to even touch the ground heat exchanger at those points. If this ground heat exchanger gets this fluid in this pipe gets too cold, the pumps connected to the ground heat exchanger can start injecting heat into that pipe. They're going to be warmer than the pipe, and because of the ground temperature. And in the summertime, if we're air conditioning a lot, we can use the ground heat exchanger because the ground temperature is cooler to absorb some of the heat that's being rejected by the school or by the other buildings. So basically, looking at what I'm suggesting is that there's enough heat available from a twin pad ice rink to be able to heat roughly 200,000 square feet of building plus another 109 homes that are surrounding it. And basically what happens is that the ground heat exchanger is there to absorb heat when it can't be used in any of the buildings, or to provide heat when heat is needed and it's not available from the refrigeration system. The heating and cooling loads don't always coincide exactly, so the ground becomes basically a storage tank for the excess energy. So basically, for most, pretty much any client I've ever dealt with, they want to see a reasonably good return on their investment, and it's really important to look at a holistic design approach. Really have a good understanding of how much heating and cooling you're dealing with, and what can potentially be done with it. So looking at providing a solid rate of return on a client's investment, that's the only way that people are going to start using it or start adopting these kinds of systems. Making sure that the system is well designed. It's not going to overheat in time. It's not going to freeze up in time. So it can be designed in such a way that it's actually much more reliable than a conventional gas boiler and a chiller. And again, the CO2 emissions, if the design is improved, you can increase the CO2 emissions reductions and basically maximize and optimize the performance of the system. Again, the systems like this can be designed for almost any kind of application. Projects have been done in the Australian outback, where the ground temperature is about 28 degrees C, about 20 degrees warmer than what we see. And there have been systems that have been built in a place like Anadyr, Russia, where they're taking heat out of permafrost. So there's a lot of applications that can be done. There's applications surrounding you in Winnipeg. Applications, JFK Airport is looking at installing a system in their new 3 million square foot terminal. The Obama Library is installing a geothermal system in their 250,000 square foot building in Chicago. Okay, well, thank you for your time. Does anybody have any questions at all?
For questions, just make sure that you take yourself off mute. And if you want to, you can just put a star in the chat and then we can call on you. Oh, no questions, anybody?
This is Chris Archer. I couldn't find the chat, so I have to speak. Can you hear me?
Yep.
I'll say, okay, great. I was wondering what was the model tools you used for the ground temperature with the plot you had, and I guess that extends to what was what you used for the buildings, and then after the system is built, what type of operational control and monitoring is needed to make something like this successful?
There's several kinds of energy modeling software that can be used, that I've seen used successfully for ground source systems. There's IES, Train Trace, Carrier HAP, Energy Plus. They're all can be used effectively, and as long as you're pulling the right, exporting the right kind of loads that you need for the ground heat exchanger design. But we're typically using Train Trace, but there's, like I said, there's several other pieces of software that can be used, have been used successfully. For the ground heat exchanger design, there's also a couple different design softwares available. There's ground loop design is probably the industry standard, but there's also another product called LoopLink that's available online. There's also a couple other ones called GLEPro, GLHE Pro, and another one out of Europe called Earth Energy Designer. They all use basically the same types of algorithms. Some are a little bit more user-friendly than the other. Again, the ones that we use are in our office is GLD, or ground loop design. For the long-term operation of the system, basically, because you're the designers, you're working with basically a utility with the energy in the ground. You've designed an energy source and a heat sink. You're basically designing a replacement for a gas pipeline and a replacement for a cooling tower. So it needs to be sized appropriately. And you want to make sure that the system is going to continue working properly. There's a number of things that should be considered. Potentially, if you've done any amount of energy modeling, you're probably aware that they're not always 100% accurate. And you may not have all of the information that's needed initially to get the proper loads for the system. So at best, you might be getting within 5 or 10%. So monitoring how much energy that you're actually putting into the ground or pulling from the ground on an annual basis is really strongly recommended. So basically what that means is installing a flow meter on the pipe going to the ground, and a temperature sensor in and out of the ground, so you can actually recreate an energy model based on the actual use of the building that's been built, and based on the weather that is from differences from year to year. So you can have if you're monitoring it like that, you can continually update the energy model, and that would take into account with different weather from one year to the next, or different occupancy of the building. And then if you have that information, you can actually predict what the ground temperature is going to be over the next week, next year, next month, or even 5 years from now. So you can anticipate that the ground heat exchanger may start overheating because of the way because of potentially climate change, or because of changes in the way the building is being used, or because of an inaccurate energy model. And you can react to it. One of the benefits of a ground source system is that you are working with basically a storage system, so you've got time to react to it. Does that kind of answer the question that you had?
Yeah, that's really good. Yeah, there's all, yeah.
Okay.
Thank you.
Okay. Any other questions from anybody?
Okay, I can ask one more.
Oh.
Okay.
Laura, did you have someone else?
There's just some questions here in the chat.
Oh yeah, okay, do those please.
So
Okay,
we have a question from Dennis. What would a system like this cost?
the cost of a system, if it's well designed, one of the, assuming that you've got a good energy model and have had the opportunity to work with the architect, with the building owner and the architect, and with the mechanical system designer, and potentially even the electrical engineer on the project, you can actually change the building loads. If you've done a good energy model to start with, you might find that the loads are not as well balanced as you'd like them. And let's say the cooling loads are much bigger than the heating loads. Some of the things that could be done is specifying different types of glass that have a better solar heat gain factor. Looking at the lighting and lighting controls, you might want to consider daylight sensors. Might want to consider how the ventilation air is supplied to the building. If you're supplying straight air, fresh air from outside at minus 30 degrees, that's going to have a large impact on how much heating that you need to do. It's also going to have an impact on how much cooling you need to do the following summer. So if you can consider looking at a heat recovery ventilation system or energy recovery wheel or whatever, you can reduce those loads. And often what we're finding is that the cost savings on building the ground heat exchanger more than offset the cost of the energy efficiency measures you might want to consider on the building. So in other words, it might cost, let's say $100,000 to put better glass into the building, but it might reduce the size of the ground heat exchanger by $130,000. So you're looking at for those kinds of offsets, but you really need to take the opportunity to work with the architect, with the mechanical system designer, with the electrical engineer, and with the building owner. It's a much more holistic approach that really needs to be taken. And the only way you can do that with any kind of reasonable accuracy is by developing a fairly accurate energy model to start with, and then do several iterations of the energy model, building in energy efficiency measures. So that, if you can take that kind of approach, we're looking at simple paybacks in a lot of buildings, probably 3, 4, 5, 8 years, somewhere in that range. Even with the price of gas and electricity in our climate, we just finished 3 feasibility studies for the city of Toronto in the last year. 3 buildings ranging in size from about 75,000 square feet to about 175,000 square feet. One of the buildings is on the screen right now. It's the Waterfront Centre in Toronto, and they were looking at about a 5 or 6 year payback, if I remember correctly. So and the only way we achieved that was really getting a good energy model of the building to start with, and then creating several iterations of the energy model, building in various energy efficiency measures, and getting to the point where the energy loads are balanced, and that's going to result in the smallest ground heat exchanger. So might be looking at a cost of the ground heat exchanger typically might be about $3 to $4 per square foot of building, somewhere between, let's say, about $3 and $6 per square foot. Yeah, in the projects I've worked on in Manitoba. Same with the projects I've worked on in Minnesota or in Southern Ontario, roughly somewhere in that range. So 100,000 square foot building, you might be looking at maybe $350,000, $450,000 more incremental cost compared to installing a conventional gas boiler and a chiller. So somewhere in that range is typically what we're seeing.
All right, thank you. So the next question is from Lohrenz. For sites adjacent to the lake or river, how does this affect the options for design?
Can you repeat that?
So for sites adjacent to a lake or river, how does this affect the options for design? That,
in some cases, that can be a really good opportunity. There's systems that have been, heat exchangers that have been installed in a lake or in a river. In fact, at the Forks, there's a heat exchanger in the river that's providing some of the heating and cooling for the Forks market. There's schools in northern Saskatchewan that have heat exchangers built in the lake that have been operating for several years. There's a large hospital in, let's say, Burlington, Iowa, for example, probably about a 600,000 or 700,000 square foot building, and they've got about a 15 or 18 acre pond adjacent that was built initially just for aesthetics and stormwater management, and they designed it a bit larger and built a heat exchanger in the bottom of the pond, and then let the pond gradually fill up. There's people that have installed heat exchangers in the ocean. There's a college on Vancouver Island. They've got about an 80-ton system heating and cooling the residents. So that can be a really good opportunity in the right kind of situation. And one of the options that was being considered for the Waterfront Center building, that's on the screen right now, it's adjacent to Lake Ontario, right on the shore, and they're looking at a surface water heat exchanger right in the lake, right beside the building. So it can be a really good opportunity, and it can be in some cases less expensive to build than a vertical heat exchanger, for example.
Great, thank you.
Okay.
So,
okay.
Is there a firm that you would recommend for a residential project? And they're also wondering about a budget for a 2,400 square foot home.
Haven't been involved very much in residential projects in the last number of years. Typically, in a 2,400 square foot home, I would have to guess you're going to be in the range. It's basically the cost of the heat exchanger. That's the incremental cost. So heat exchanger, depending on what kind of heat exchanger you can build. If you're looking at a horizontal ground heat exchanger, if you've got a little bit bigger property, it might cost an additional $7,000 or $8,000 or $10,000, somewhere in that range. If it has to be a vertical loop within the city, it might be looking closer to $12,000 to $15,000 additional cost. Compared to electric heat, you're looking at a total energy cost saving of roughly 50% on your total electrical bill. If you're comparing it to natural gas right now, you're looking at a smaller saving, probably in the range of maybe 30, 35%. You're getting some saving on cooling. On a house, you don't do as much cooling as you would on a commercial building, so you're not getting as much saving there. But for a commercial building, you're going to get a lot more saving on the cooling. If some of the projects that we did in Toronto, where they got very expensive electricity, somewhere in there for the commercial buildings, probably 15 cents a kilowatt hour. The price of the gas is about the same. We're looking at really pretty cost effective, because the cooling loads are so much higher in a commercial building. Residential buildings, you're probably looking at about a 25 to 35% energy cost saving compared to natural gas in Winnipeg. Probably in the cost, like I said, depending on that size of the house, it might be an additional cost of maybe probably $10,000 to $15,000, somewhere in that range.
Okay, thank you. We have another residential building question. So are residential building owners accepting of adding geo to their home? And do they need to improve their home energy first?
Ideally, the approach that I would take on a residential building is very similar to what I would do with a commercial building. You really want to understand how much heating and cooling you need in that building, and it's going to certainly benefit you if you can reduce the heating loads at all. Because the cooling loads are so low in this province, you might consider with the kind of glass that you're installing in the building, it actually might be better to install the clearest glass that you can to allow the solar heat to enter the building as much as possible, which would increase your cooling requirements in the summertime, but it would offset the heating requirements in the winter, because you're dumping heat back into the ground all summertime. In my own home, for example, I don't have a lot of cooling load. What I've done, a system has been installed since the early 90s. I've added a solar thermal system on the roof, where during the summer, I'm rejecting heat into the ground, taking solar heat and dumping it into the ground as much as possible, and to make the heating in the winter more efficient. It's been running since last summer. Looks like it's added a couple of degrees to the ground temperature for this year, and expect to do a bit better the next year. But again, balancing the loads as much as possible by considering the kind of glass that's being installed, by considering the efficiency of the heat recovery ventilation system that's installed. Anything you can do to reduce the heating loads, and actually may want to increase the cooling loads to help balance the loads, and that's going to be a benefit. Looking at the orientation of the house, that's going to be can be a fairly big factor in some homes.
All right, thank you again. So another question here. So Northlands DFN in Lac Brochet has a lake-based heat exchanger in its biomass. Oh, that's not a question. That's just a statement. Never mind.
Okay.
So for those who didn't know, Lac Brochet has a lake-based heating exchanger in its biomass system. Okay, so here is another question. In the district heating and cooling systems, oh no, that moved. Sorry, in the district heating and cooling systems, what are the participants' cost models? Something like the Whispering Pines development in Texas or the rail yard projects in Winnipeg.
There's a number of different ways that people that are in those developments end up paying for the cost of the system. The Whispering Pines development, I believe, is sort of a utility-based system where a third party is building, owning, and operating the ground heat exchanger connected to each of the homes, and their homeowners are charged much like they would by an electric or a gas utility, by how much energy they're taking from the system or dumping back into it. Gibson's BC has a similar system where the town has actually created a geothermal utility, and the homeowner in that case is being billed on a per square foot basis. It's kind of interesting what's happening in Boston these days, because some of the gas lines in Boston are probably 80, 90, 100 years old, and they're starting to leak. In fact, in some of the streets, they're leaking so badly that it's actually killing the trees on some of the streets. So they've got the option of replacing very expensive gas lines that have traditionally been amortized over about 85 years. The problem that the gas utilities are running into is that the state has mandated that they're going to be not using natural gas after 2050. So the numbers simply don't add up. They can't amortize the cost of the pipeline by the time they've got left to sell the gas. So what they're actually starting to do is two utilities that are starting to do this utility called Eversource and another one called National Grid, very large utilities. And they're starting to look at installing geothermal pipes that can connect to the buildings that they run past, installing pipes under the streets instead of installing gas pipes. So they're basically actually going away from natural gas and starting to install geothermal utilities, taking advantage of the heat in the ground, and actually in a district system like the hypothetical one at the Dakota Community Centre, you can actually take advantage of the waste heat from an ice rink, or from a data center, for example, or any kind of other type of system, any kind of manufacturing plant that has a lot of waste energy that can be rejected into a district system and provide heating and cooling for the buildings connected to it. There was a study done recently for the city of Woodstock, Ontario, for about city of about 40,000 people, and looking at the potential, if it was possible, to design a ground source system in an existing building or existing city and create a geothermal utility. At this time, the cost of electricity for residential in Ontario is about 18 or 19 cents a kilowatt hour, so it's very expensive. The price of gas is about the same as it is here, roughly the equivalent of about 3 cents per kilowatt hour. So right now, the numbers are pretty challenging to make them work. But I suspect that's going to change over the next number of years as gas utilities start becoming geothermal utilities. There's probably half a dozen or a dozen cities in the U.S. that have banned the extension of gas pipelines. Hasn't happened in Canada yet, but with pressure from environmental groups and from all kinds of places, I suspect that will gradually change.
Okay, so now we have a question from Don. Do you see a greater interest in this larger neighborhood design coming, or something that still needs more education and marketing to the building community / municipalities?
There are more and more district systems that are actually being built. There's at least 3 or 4 university campuses that have already got systems in operation. Ball State University in Indiana, I think it is. Missouri State University of Science and Technology in Missouri. There's a university campus in Grand Junction, Colorado, that's got about 16 or 18 buildings connected to it. They started that about 10 years ago. There's a number of residential projects that are going ahead. So yes, absolutely, there's a lot more interest in it. And there needs to be a lot of education in how to design even a single family or a single building system, simply because there hasn't been much emphasis on good energy modeling with any of the with very many firms across that I've run into across North America, or even outside of North America and Europe, or certainly not places like Australia as well. So there needs to be a lot more emphasis on really understanding buildings well, and then taking advantage of the power of those kinds of tools to really inform the designers of the building on how best to make these systems, to optimize these systems.
All right, well, thank you for all of these wonderful answers that you've been providing. This is the last call for questions.
I have a question, Laura.
Go for it.
Ed, this is really inspiring stuff, what you've shared with us here. In your example with the Dakota Community Centre, unless I'm misreading things, it looks to me like there was heat added into the system primarily by the ice makers at the skating rink, correct?
That's right.
And most of that is during the winter.
Yep.
And even though you did your analysis, and the thing is that system was still adding heat over time, was gaining heat over time. Is there not a way to use the cold air in the wintertime to reduce the amount of heat that the ice maker is adding to the system, so that you can get away from this ultimate buildup of heat? Is there some way that you can incorporate that?
Probably the most beneficial way to do that is add more buildings that require heat. If you simply can't find more buildings that require that can benefit from the heating, then you can look for some other beneficial uses. The IKEA store in Denver, for example, they've got about, they're in a position where they have to get rid of about 10 times more heat from the building than they use in the building. They can't use anywhere near all the building that the heat that they're taking from the building when they're air conditioning. So what they ended up doing is installing a snow melt system in about 35,000 square feet of loading dock area and second floor, a ramp to the second level loading dock area. And that basically becomes a big concrete cooling tower. And it's primarily designed to get rid of heat, but if it snows, it happens to melt snow as well. So it provides an additional benefit for the building owners, and they avoided the use of actually building a cooling tower, which requires a lot of water for evaporation, depending on the type of system you're looking at. So it provides some more benefits. If, for example, you're looking at a multifamily residential building and you've got a lot of excess heat, if you've got let's say a lot of buildings with condominiums with a glass curtain wall, for example, end up absorbing a lot more solar heat, and they have to do a lot more cooling than they do heating. Using that to melt snow at the front entrance, for example, a ramp to the basement parking lot would be a good thing. Adding the domestic hot water loads for the building to a building like that is a really big benefit. It provides domestic hot water, eliminates the use of gas for making hot water, and actually can reduce the size of the ground heat exchanger as well as improve the long-term performance of it.
Got it. Thanks, Ed. So just make more use of the heat is what you're saying.
Yep. Exactly.
Put it to better use. Got it. Okay.
It's better to find a beneficial use for the heat to avoid gas anywhere else than pay good money to run fans and pumps to get rid of it.